These are the notes for day 97, section 9.3. There are two ways to test for convergence, the integral test and the p-series test. The first one, the integral test, can be applied when you have a continuous decreasing function that can represent the sequence of terms. So if a sub n is the sequence of terms, if you can create a function that goes from 1 to infinity, find the antiderivative of that, and as long as your function is continuous and decreasing, both the sequence and the antiderivative will converge or diverge. It's important to note that the value that you get from the antiderivative is not the same as the sum, but you will know whether or not they converge or diverge. So the example here is a good use for the integral test because if you look, I can let u equal n squared and du is going to be 2n dn. So this antiderivative is reasonable. We just have to check the conditions first. So first condition is it positive? Well, we know that this function is positive. E to the anything is always positive, and multiplied by n, which is only positive values because we start counting at 1 will always be positive. Is it continuous? Yes, there's no domain restrictions. And is it decreasing? I'm going to take the first derivative, factor out an e to the negative x squared. This term is positive, and this is negative whenever the value of x is 1 or more. So when we have a positive times a negative, we get a negative. First derivative is always decreasing when x is greater than 1, so our function is positive, continuous, and always decreasing. So I can use the integral test. I'm going to take the antiderivative of this sequence formula with the n's replaced with x's. Antiderivative winds up being negative 1/2 e to the negative x squared. I'm going to substitute in t and 1 and let t approach infinity, and we get a finite value of 1 over 2e. Since that's a finite value, the antiderivative converges or has a finite sum, therefore we know that the series converges. But again, it's important to know that just because the area under the function is a known quantity, we don't know the sum of the infinite sequence of terms. So we know that it converges, we just don't know what it converges to. So very important is a summary of what I just said. The integral test limit does not produce the infinite sum value. You should try to get the partial sums and let n approach infinity. Often this is quite difficult to do, so in our class we don't find the partial sum formula and we don't find the convergence value. The second topic is called p-series, and it can be applied to reciprocal functions. There are three reciprocal functions that we've studied before, 1 over x squared, and 1 over x to the third. And in chapter 8, we learned how to take the antiderivative of improper limits, and we found out that 1 over x diverges. This sum underneath the curve from 1 to infinity is infinite. But for 1 over x squared and 1 over x to the third, we get finite sums. So when I change my function to this blue one here, 1 over x squared, from 1 to infinity, the area under the blue is 1, and 1 over x cubed, which is now blue in this graph, if I start at 1 and go up to infinity, the area under that is 1/2. We have proofs for what happens in y between 1 and higher than 1 in chapter 8, and those are some homework problems that we'll go over. But the overall conclusion is that using the integral test, we now know that reciprocal functions where the exponent is 1 diverges, and anything bigger than 1 is going to converge. So to summarize on the next slide, the common application of the integral test to reciprocal functions is called the p-series. 1 over your index value n raised to some constant value p is a p-series, and this will converge if your p is greater than 1, diverges if p is between 0 and 1, including 1, and the special case p equals 1 is called harmonic. So we're just going to go through 4 quick examples here. Here's a p-series. The p-value is 2. The index is n, so the n changes from 1 to 2 to 3, but the exponent is always 2. Since 2, the p-value, is greater than 1, we know that that converges. In this case, root n is the same thing as n to the 1/2. That's a p-series with n equals 1/2. That one diverges. Here the exponent is 3/2, larger than 1, so that converges. And the last one, sorry, I didn't write these down. And the last one you should try on your own. Here the exponent is 1/3. And so if it's 1/3, we know that it diverges. So again, to summarize what we just saw, P-series is when your index is in the reciprocal, is in the denominator. So the index is going to be increasing 1 over 1, 1 over 2, 1 over 3, 1 over 4, and your exponent stays the same. Sometimes this gets confused with geometric. In geometric, your index is in the exponent, so the exponent is going to keep increasing. N equals 0, n equals 1, n equals 2, etc., etc., etc. So try and keep those separate in your head. Different rules for those two situations.